Section 12.1, we're going to talk about inference procedures for regression. So confidence intervals and hypothesis testing. Okay, so here we have a scatter plot. The old faithful geyser in Yellowstone National Park, they collected data on the duration of the eruption and the time between it. They collected data for all 263 eruptions in a month. So this line is a population least squares regression line because it contains all the data for the entire month. And then we have sigma equals 6.47. So that's the standard deviation of the residuals for this line. Last chapter we had this as S, and that's because we were using sample data. Because this is population data, they're using sigma, but it's still the standard deviation of the residuals. Okay, so some symbols and things that we need to know. If we are able to make a population regression line, okay, where we have data for the entire population, mu y is the mean y value, okay, beta 0 is going to be our population y-intercept, or you could just say b0, and then beta 1 is our population slope. Okay, everything that we did in chapter 3 was sample regression lines because we were working off of sample data. Okay, so here we have different samples, which is what we were doing last chapter. So we took that population data, and instead of using all 263, we took samples of 15 of them. And as you can see, we get a slightly different regression line every time we take a slightly different sample, which totally makes sense. So what that means is it would be helpful to have some information about the sampling distribution of slope. So if I could take all of the possible samples of 15, what would those different slopes look like? And it ends up that they look like this, which you should recognize as approximately normal. Okay, so characteristics of the sampling distribution of slope, it is approximately normal. The middle, the center, the mean is also the slope of the regression line, okay? So this B slope is an unbiased estimator of population slope because the center of the sampling distribution is at that mean value. And then here's how we find the standard deviation, okay? It is the standard deviation of the residuals divided by sigma x is the standard deviation of the x values for the population, all right? And that's how we get the standard deviation of the sampling distribution. So these are the characteristics that you need to know. You need to know what the mean is, you need to know how to find the standard deviation, and then you should know that it is approximately normal, okay? Most of the time, as you've seen throughout this class, we do not have access to population data, so we can't find a population regression line, but what we can do is take some sample data and find a good estimate for our slope. Okay, so we can do a confidence interval for the slope of a regression line. So here we've got this truck data that we use as an example in chapter 3. We did some regression analysis. We've got a line of best fit for a least squares regression line. We've got a residual plot. And then this is a histogram of the residuals. So we're looking at the relative size of the residuals, okay? And we are going to construct and interpret a 90% confidence interval for the slope of the population regression line. Okay, again, this line is based off a sample of 16 cars. If we were somehow able to collect data for every car, what would that slope look like? That's what we're trying to figure out. Okay, so same SPDC that we did for all of our other confidence intervals. Okay, so we're going to state the confidence level that we're doing, the parameter that we want to estimate, which in this case is B1, slope of the regression line, and then the parameters that we use in the regression line. Basically, what are your X and Y representing? Okay, so we're doing a 90% confidence interval for beta 1, the slope of the population regression line, relating Y equals price to X equals miles driven. All right, plan. The procedure that we're doing is a T interval for the slope, and then the conditions that we have to check. Okay, to do a confidence interval for slope, We actually have 5 conditions that we have to check. All the other things that we've done have usually been 3. This one has 5, and we can use the acronym LINER to remember what they are. All right, so is the relationship linear, independent, which is also basically our 10% condition? Do we have approximately normal? Do we have equal standard deviations? And then are the data random? Okay, so we'll talk through what each of these specifically means. When we're checking the linear condition, we're looking at the scatter plot to see that it like makes a general line shape. And then we can also look at the residual plot and make sure the residual plot doesn't have any curve patterns. So like this one, if I'm looking at the scatter plot, that would be a check for my linear condition. This one would not, because that residual plot has a very clear curved pattern. Okay, independent are, and when we're talking about this, we're not saying are the x and y variables independent, because most of the time we don't think they are. That's why we're doing this regression analysis. But more, does one y value affect the size of another? Okay, and so basically what we're looking here is we're checking that 10% condition to make sure that that is true. Okay, then normal, they suggest that we make some sort of graph of the residuals to look for skewness or outliers. Generally in the computer output that you're given in a problem, you'll get like a histogram or something, and we're just looking at that to make sure there's no strong skew. Equal standard deviations, okay? When we look at the residual plot, we want it to basically not have a pattern. We want it to kind of be like equal above and below, nothing crazy going on. Whereas if we look at this residual plot, when I have low x values, I have very low residuals. Everything is close. But then as my x values get higher, my residuals tend to get larger. Okay, and that would not pass this equal standard deviation condition. And then the last one is random, just whether or not our data came from a random sample. So let's go through those for our truck example. All right, so we have given to us in the problem, they gave us a scatter plot and the residual plot. So for our linear condition, scatter plot is linear and residuals have no patterns. Check on that one. All right, next one is independent. We're gonna say it's reasonable to assume that 16 is less than 10% of all the Ford F-150s. Okay, normal, in our computer output, they gave us a histogram of the residuals. There's no huge, strong skewness or outliers in this histogram, so we're good there. Okay, equal standard deviation. If I look at this residual plot, it's roughly the same from the left side of the graph to the right side. There's no pattern there. And then random, they told us in the problem that they took a random sample. All right, so all 5 of our conditions, LINER, are met here. So then we get to the do part where we have to actually calculate the confidence interval. Okay, this is the formula that is on your formula sheet. All right, so we would be looking for the standard error of the slope, and that's what would go on the bottom there to be able to calculate our confidence interval. All right. Um, here's kind of what we were looking for. B, which is our slope from our sample data, plus or minus T star, which is the same that we've been doing, times the standard error of the slope. Most of the time, you're not going to have to actually find this because it is given to you in that computer output. Okay, so here's our computer output on the regression analysis. Here's my slope for my regression line. Okay, we've already talked about where to find that. And then the standard error of the slope is the standard error of that coefficient. So in this case, 0.03096. So your calculator, if you have a TI, it can do T intervals for slope. The Casio cannot. But honestly, you would have to type in all of that data. You have to type in the data in the lists. So if they give you computer output like this, I wouldn't bother. Even if you have a TI, just use the computer output. It's going to be faster. Okay, so degrees of freedom is n minus 2. Okay, I find my t star using inverse t, just like we did in earlier chapters. Okay, and then this negative 0.16292, that was my slope from my computer output. And then that's going to be plus or minus t star times the standard error of the slope, which again came from my computer output 0.03096. Okay, so here is my confidence interval for my slope, and then we write our conclusion sentence, same as before. We are 90% confident that the interval from, and then you give your context for the problem. Second thing we can do is we can also do a significance test. I'm going to talk through this as fast as I can just so this video doesn't get too long, but please feel free to pause, rewind, watch things again. Make sure you read through this example. Okay, so we want to know, is there evidence of a positive linear relationship? So is our slope positive? That's what we are doing a hypothesis test for. Okay, so SPDC again. Our hypotheses are going to be that B1 is equal to some value. It's pretty much always 0. If it's not 0, we have to make some adjustments. So it's rarely that they ask some specific number. Okay. So in this case, our null hypothesis is that the slope is 0, and then our alternative is that it is greater than 0, because that's what we're testing. Is it a positive relationship? Okay, and we're defining that slope and y and x just like we did with our confidence interval, and identifying our level of significance. Okay, plan, it's going to be the same thing. Our procedure is a t-test for the slope, and then our conditions are that liner acronym again. Okay, so linear, we got a linear pattern in our scatter plot. We've got no curve patterns in our residual plot. Independent, we can assume that 38 is less than 10% of all infants. Normal, here's our histogram of residuals. Nothing crazy there. I know there's a little gap here, but that's not a huge outlier. Those values are still close, so we're good there. Equal standard deviations. Again, we're pretty evenly spread out here on my residual plot. And then random, they told us that it was a random sample. All right, so now we have to find our standardized test statistic and our p-value. Okay, 3 different ways we can do this. One is formula. Okay, so this would be it. T is equal to b minus the hypothesized slope, usually 0, divided by the standard error of the slope. Okay, and then again, our degrees of freedom is going to be n minus 2. We can use the calculator. All right, Casio will do this one. The thing here, though, is again, you got to type in the entire data set, which if we get larger than 7 or 8 numbers can be really time consuming, could take away time that you need on an AP exam. And it also gives you an opportunity to make errors, any sort of typo there. So I would recommend, just like we did with the confidence interval, using the computer output. Okay, they give you your t statistic. Okay, coefficient, standard error of the coefficient, and then t. There it is, 3.07. So that is my t value that I would write down for my do step. Okay, the p value that they give you is for a two-sided test. Okay, so if your alternative is that it is not equal to 0, that's your p-value right there. If your alternative is that it's less than or greater than 0, then we have to divide this number by 2 because this is the p-value for a two-sided test. Okay, so what you would write is the t statistic, and you would just get it straight from the computer output. And then the p-value, if we're doing a one-sided test, go ahead and show that we're dividing that number by 2. If we were testing that it is not equal to 0, then again, you could just say the p-value is equal to 0.004, and we'd be good. All right, and then conclusion, same as before, we're going to reject or fail to reject, and then say whether or not we have evidence. So in this case, because our p-value is less than alpha, we're going to reject the null hypothesis. So we do have convincing evidence of a positive linear relationship, aka that our slope is greater than 0. Okay, and that's it for 12.1.